Question 3. The Doppler effect. Doppler ultrasound can be used to measure the speed at which blood flows along blood vessels. This is important in the detection of diseased blood cells. Ultrasound has a frequency too high to be detected by human ears. If a source of waves is moving towards a detector, explain why the wavelength detected by the detector is less than the wavelength of the source. Okay, so this is really, it doesn't matter about any of the context in this. All you're looking at is explaining how the Doppler effect works to produce less or lower wavelength. So wavelength is decreasing as it moves, as the source moves towards detector. Okay, so the main idea is, if this is the source is releasing waves. If it's stationary, they just travel out and nothing unusual happens. But if the source moves, so here's the detector here, it's reading the waves. If the source moves towards the detector, subsequent waves are released closer to where their position would have been relative to the next wavefront that's already passed out. So it has the effect of them compressing on this side and stretching on the other side that it's moving away from. So that's just the Doppler effect in a bit of detail. B. An ultrasound wave is sent along a blood vessel and the moving blood cells reflect it. The blood cells effectively become a source of sound waves. So now we've got the blood cells being a source, and yeah, it's moving at the speed of the blood. Because we're trying to find the speed of the blood, yes, down here, calculate the speed of the blood cells. So you have to start anticipating, as I usually talk about doing. So setting up the whole situation in your mind to get it very clear. So in this situation it's the same as above, where we've got the detector over here. This is my version of a detector, we'll call it D, and the source is moving towards that detector. So in our Doppler effect equation, I don't know if we need to use this, but I'll put it up here. F dash is F, and then you've got the velocity of the wave over the velocity of the wave plus or minus velocity of the source. Now since it's moving towards it, excuse me, it's going to be a minus, and so that means this will be minus. And that's because you're decreasing the wavelength, so you must increase the frequency to have the velocity the same, from V equals F lambda. So except it's the other way around from how I've drawn it here. The wavelength is decreasing as they compress, as it moves in that direction closer. That means the frequency has to increase. So to increase the frequency, in our equation over here, the frequency must be multiplied by something that's greater than or equal to 1. So that means the bottom has to be less than the top, and the only way to do that is if it's using the minus. Okay, you can replay the video and follow that through again, but basically you want this term here to be greater than 1, otherwise the frequency doesn't increase down the bottom left here with the corresponding decrease in wavelength. In any case, that's just anticipating, thinking ahead. The speed of sound in blood is 1,545 meters per second. That's the velocity of the wave, the sound wave. The blood cells reflect sound waves at a frequency of 1.0522 times 10 to the 6 hertz. Okay, so which frequency is that? Is that F or F dash? Is that the frequency that's been modified, or is that the frequency that the source is putting it out in real time? So this is the blood cells reflect sound waves at a frequency of it. So that would suggest to me that it's this, that it's not the modified value. Otherwise it would say the detected wave by the Doppler is this, but it doesn't. It says that's the sound waves reflected at the frequency they're reflected at. So this is F. Okay, carrying on. Because the cells are moving, the wavelength is Doppler shifted, of course, we know that. The reflected sound is detected with a wavelength of, okay, see there? The reflected sound is detected with a wavelength of 1.467 times 0 times 10 to the minus 3. So we know that this is the modified wavelength, if we like. We'll call it wavelength dash. So I think we've got enough information to answer this question. We've all set it up, so I better change colour for the actual working. Now we're trying to find the speed of the blood cells, which is Vs, velocity of the source. So let's write that as a question mark. So it looks like we can use this equation to find out what we need to find out. We've got the unmodified frequency, we've got the velocity of the wave, we just need the frequency that's been modified. From our wave formula V equals F lambda, we have the modified wavelength, and we have the velocity of the wave, which would be Vs in this case. Sorry, Vw, velocity of the wave, not velocity of the source. And we know the frequency. So, sorry, no, we don't. Yeah, this case, this is F dash that we're trying to work out because we're using the modified wavelength. So, I don't know if I'll perform the calculations, but I'll show you how we do them. We would have, because we're trying to find F dash, so we rearrange. F dash equals velocity of the wave divided by the modified wavelength, and the modified, and that's 1545 meters per second divided by 1.4667. My dyslexic kappa's on this morning. I have to be careful. So where are we? And that was times 10 to the minus 3. So you'd plug that in to find F dash. Now you've got F dash, and you've got F, and you've got velocity of wave, but you don't have velocity of the source. So now you just need to substitute everything in and rearrange to find velocity of the source. And I'll show you how that goes. And again, I haven't calculated the actual values, so you can do that yourself. The main thing is the process, learning the process, and then you can practice and make sure you get the process correct by checking with the answers. We've got the formula F dash equals F velocity of the wave over velocity of the wave minus velocity of the source. Remember, we just explained why it was minus. We want to get Vs by itself, so the only way to do that is multiply by these bottom brackets, both sides, so that we can get it off the bottom. So Vw minus Vs times F dash equals Fvw. And expanding this out will be F dash Vw minus F dash Vs equals Fvw. So now, because we're just wanting to find Vs, we can get rid of some of these terms and shuffle them around a little bit. If we add, since it's a negative term, if we add that to both sides, and if we want to take this away from that side, that way we will get this term here by itself. So I'll do both steps just to make that clear. We've got F dash Vw equals Fvw plus F dash Vs. So remember, that's one we wanted. We just added that to both sides. That cancelled out on the left and gave it to us on the right. Now we want to take this term away. So we're going to go F dash Vw minus Fvw equals F dash Vs. Okay, and now there's a couple of things we can do, because remember we're trying to get Vs by itself, so we can divide both sides by F dash and then see what we get. Or let's just do that. F dash cancels there, so we end up with the velocity of the source equals F dash velocity of the wave minus F velocity of the wave divided by F dash. Okay, looks kind of tricky. The process was a little bit awkward, but now you just plug the numbers into that and equals, and you would get the velocity of the source of about 1.47 meters per second. So you can work through that yourself.